Hi, this is Kevin. Welcome to my lecture on um, the Python objects chapter of the Severance Python for Everybody textbook. Let me get my slides going. Um, he has a warning here, which I'll leave for you to read on your own. Okay, so the main point that we want to make to begin is Python is a very object-oriented language, and we've been using Python objects all along, right? And even the basic value types uh, that we use, uh, ints, floats, strings, booleans, they're all instances of classes, and as such, they're programming objects. So we've been using objects a long time, okay? And in addition to that, we've been using some more complex objects like lists, okay? So we're looking at some of the documentation for the list class and list objects right here. And there's a link to the, I guess this is the Python 3 tutorial on data structures, which includes lists, which is the most popular of the Python 3 data structures. We might also want to use packages that kind of add on to basic built-in Python. Okay, and here we're using the example of SQLite 3, which is a package that allows Python to uh, connect to relational databases, SQL-based relational databases. Okay, and nearly every package, in addition to having functions, includes classes. And as we use them, we create instances of those classes, and those instances are programming objects. So here we imported the SQLite 3 package. We called connect, which is going to get us a database connection object, and then we're keeping a reference to that object in the variable con. Okay, so objects are all over the place. So let's start with programs. Okay, so here's a program. Maybe not in the exact form that a program would appear in my class, where we tend to put all of our code in a function called main, and then we have at the very bottom a method called main. But this is a more script-like program, more typical of what you might find in a textbook and what you do find in the Severance textbook. So let's see, we call the function input, and we prompt the user Europe floor. Okay, and then we save the response in the variable imp, and then we take imp and we call int on it, and we add 1. Okay, so calling it is going to turn it into a proper int, and adding 1 is going to add 1. And then we get, we store that in USF, which I guess means US floor. and then we print US floor, USF. And although not everybody knows this in Europe, um, the ground floor is not the first floor. Typically, they call it the ground floor. And what we call the second floor in the US is what they call the first. And so here we have the use case for the program. And, we did the typical input, process, output. So the first line was input related. The middle line was process related, and then the bottom one was output related. And there are a number of objects here. Most notable are the objects that are pointed to by INP and USF. Okay. So, in Python and in any other object-oriented language, a program is made up of many cooperating objects. Instead of being the whole program, each object is a little island within the program and cooperatively working with other objects. A program is made up of one or more objects working together. The objects are making use of each other's capabilities. So what's an object? Well, and when we say this, what's a programming object? Okay. So a programming object is a bit of self-contained code and data. A key aspect of the object-oriented approach is to break the problem into smaller, understandable parts. To divide and conquer, as it were. Objects have boundaries that allow us to ignore unneeded detail. And we'll see an example of that in a minute, and we'll see the practical benefit. We've been using objects all along: string objects, integer objects, dictionary objects, list objects. Okay, so we might look at the program that we just did, or some other arbitrary program that we have a program that's kind of the cloud. And in the program are these objects. Here we say that there are 4. There are 2 that we know the type of. We know we have a dictionary and we have a string. And we have 2 other objects that we don't know the details on. Okay. And we can also see, and this is an important part of the artwork here, that these objects have particular interfaces, right? So between this object and the upper left, it has a relationship to dictionary, and it looks like it sends some input to dictionary and it gets some output from dictionary. Okay. It also has a relationship with string, and again, it sends some input to string and it gets some output from string. And it has a relationship with this other object, and all we know is that it sends output there. Okay, and then at least in theory, the input for the program is somehow being consumed by the object on the upper left, and the output is somehow being produced or emitted from the object on the lower right. Okay. Now, we said objects are bits of code and data. And that's what's one of the really promising aspects of them, and was pretty revolutionary when object-oriented programming came along and I learned about it. Okay, so objects hide the detail. They allow us to ignore the detail of the rest of the program. Now, this is kind of interesting. It's one of the features that I emphasize in my course when we talk about functions, right? Um, I tried to emphasize the fact that because well-defined functions have really specific interfaces, you know what the parameters in are and what the return uh, values that go back are. Because of that, while you're coding and testing in that function, you really don't have to worry about that function. And we're really seeing this with each of these objects, right? Um, they have specific interfaces to the rest of the programming objects that are operating in your program solution. And uh, you know what other objects can communicate with them and interact with them. And maybe you're a little worried about those, but you don't have to worry about the others at all. Um, so this architecture um, allows the rest of the program to ignore the detail about um, uh, a particular object. So let's go to some definitions. So how do we create objects in Python? Well, we create new instances of a class. Now, there are a bunch of classes that are built in, classes like int and float and string and Boolean. And we can actually create those with special syntax. But when we create a Boolean, we're creating an instance of a class. When we create an int, we're creating an instance of a class. And the class is a template that defines how an int instance works. Okay. Uh, we have method or message. So classes have methods. I don't really like to use the word message, but I'll talk to it while we're doing the slide. So methods are bits of code that are really functions that are part of the class, and we can call them and they create some action, and that action is a capability of that class. And then we have fields, right? Um, and they're also called attributes in some sense, and that's a bit of data in a class. So an object or instance is a particular instance of a class. So for instance, let's think of the int class that we use to create integers. Well, the class is a template or like a cookie cutter, okay, from which we stamp out new instances. And that's where this is the first time we see this cookie cutter uh, metaphor. Okay, and then we'll follow this throughout the lecture. So, what's the class when we look at the picture? Well, metaphorically, it's the cookie cutter object itself. Okay, it's not the cookie. It's not the decorations that have been added to the cookie. The class is the template. It's the cookie cutter. All right. Now, with the class, when we create new instances, okay, what do they correspond to? Well, they correspond to the cookie, okay? So each of these is an instance of a cookie, and it looks like there may be snowman cookies or they're Christmas tree cookies. I can't tell what this one is, but um, um, And so the cookie cutter metaphorically is the class, and then the cookie, having been stamped out, is the instance. So, some more terminology. Class. I think this is terminology that was in the Wikipedia article for class um, when the author wrote the book and created the slides. So it defines the abstract characteristics of a thing, an object, including the thing's characteristics, its attributes, fields, or properties, and the thing's behaviors, the things it can do, or methods, operations, or features. One might say that a class is a blueprint. So that's another very popular word. We can say that it's a template. We can say that it's a blueprint. Um, he says or factory, and where the definition says or factory, but the word factory has a particular meaning in object-oriented talk, and it's a bigger concept than just a class being used as a blueprint or a template. So I won't go so far as to use use the word factory myself. So class is a blueprint that describes the nature of something. For example, the class dog would consist of traits shared by all dogs, such as breed and fur color, those are characteristics, and the ability to bark and sit, behaviors. Okay, more terminology. Instance. One can have an instance of a class or a particular object. The instance is the actual object created at runtime. And I just have to say, wait, can I say this uh, down here in the yellow part? The word object and the word instance are often used interchangeably. And this is a problem in oh, the programming world generally. We generally have a kind of vernacular way to talk about something like that would be object. And then we have a more formal and computer science-y way to talk about something that would be the word instance. And the hard thing for the learner is that we who are already acquainted with it will use these interchangeably and freely, and you can get lost, okay? But when we're saying object and when we're saying instance, we mean the same thing. Okay, so in programmer jargon, the Lassie object is an instance of the dog class. The set of values of the attributes of a particular object is called its state. The object consists of state and the behavior that's defined in the object's class. So the behavior would be the methods. Okay, and I just have to warn you about Lassie here, okay? And I'm going to tell the whole Lassie story at the end, but Lassie is a character from a late 1950s, early 1960s American TV show, and Lassie is the collie here, okay, and her owner is this boy Timmy, okay, and they get into all these exploits in the episodes of the series, and they typically Timmy gets into trouble and Lassie saves the day. Uh, the most iconic of these problems that Timmy got into is that he fell down a well, And Lassie summoned the adults, and they saved Timmy. Okay, so when we say Lassie, we mean this collie dog from the show Lassie. Okay, so we say that the Lassie object is an instance of the dog class. Well, that makes sense. Okay. More terminology. Method. An object's abilities. In language, methods are verbs. And in my class, I really insist that the names that you give to methods are either verbs or verb noun phrases. Okay, that makes it easier to remember that that's the name of a method. Lassie, being a dog, has the ability to bark. So bark is one of Lassie's methods. She may have other methods as well. For example, sit or eat or walk or save Timmy. So now you get save Timmy. He's probably down the well in this classic episode, and that's why she would have to save Timmy. And she saved Timmy in just about every episode. Okay. Within the program, using a method usually affects only one particular object. So we're not calling the method save Timmy on a particular. I'm sorry. We're not calling it on the class in general. We're calling it on a particular instance. So we have a dog class, and it has, say, it has the methods sit, eat, walk, save Timmy. Okay, and we create an instance to represent Lassie. Okay, and now when we want to save Timmy, we call that method on the Lassie instance. We don't call it on the Rover instance because Rover, if the Rover instance had a save Timmy method, it would be another Timmy. It wouldn't be this lad. Okay, that's why we would call save Timmy on the Lassie instance. Okay, let's try to get to the next slide. Okay, here's some Python objects. So what we're going to do here is we're going to explore what the behavior of certain types of objects is and how you find out. Okay, so the way that you find out is that you create an instance of a certain type. So over here on the left-hand side, we are creating a bunch of instances, and so we've got X is a string, okay. Y X is a string. We asked the type of we asked the type of 2.5, so that's a float. We asked the type of 2, that's an int. We didn't assign them to variables like we did X. We create a list and we assign that to Y, so we ask the type of Y, and that's a list. And we create a dictionary and we assign that to Z, and the type of Z is dict. And why did we use such crummy variable names? Well, the author is doing an outstanding job of cramming a lot onto a slide, which is very hard if you're a courseware developer. And the author doesn't have room for more meaningful variable names. And these are all kind of arbitrary anyway. So then we do we call the function dir for directory of X and for Y and for Z. And what do we see? Well, we see here a list of all the methods that are available. And the methods that are available for string are not surprising. We've got the ones that shift the case. So we've got lower, we've got upper, um, we've got title, right? And then we have things that we use, say, for testing values. Starts with, ends with, right? So all those things. So not too surprising, but if you look at this, you'll probably find some methods that you weren't thinking were there, or you forgot about. Okay, and now Y is a list. So what are the methods available on a list? Well, append, we've used that. Clear, I don't think we've used. Copy, maybe not. Count, we've used. Sort, we've used. Okay, some of these other things we've talked about, but I don't think we've actually used them in the assignments in my class. And now we have a Z is a dictionary. So if we do dir on that, we have we've got get. We use that for sure. Okay. We've got clear. We may have used that. We've got items. This is how you get tuples, a list, a sequence of tuples with all the items. We've got keys. Here's how you get a sequence of all the keys. We've got values. Here's how you get a sequence of value objects, right? So not too surprising, but for any objects, even the ones that you create with custom classes, you can do a dir when you're down at the command line in the REPL, and you can see what methods it has. Okay, so now we're going to create a sample custom class, and we're going to kind of grow it over time. Okay, so you'll get to learn about it. And of course, we've got an even bigger and better copy of the cookie cutter and the cookies. And I'm going to say this was a snowman now, although whether it's creatively decorated. This one down here, this one in the upper right is maybe a more traditionally decorated snowman. Okay, but again, the part of the metaphor that we're trying to remember is that the class is the blueprint or the template. So that's what the cookie cutter is. And then the instance is the object that you actually stamp out, and that's what the cookies are representing in the photo. Okay, so the first class we're going to create is one called Party Animal. And probably wouldn't have been what I would choose, but I think we're trying to be fun. And the author is definitely being fun with this. Okay? So here's some of the syntax. And I'm going to show you this, and then when I get done, I'm going to show you a version that I've kind of refactored, showing some of the practices that we would use in my class and clearing up what may be a misconception or two. But every Python class begins with a header, so it has the keyword class, and then it has the name. And you know, you'll find that people who have come from other programming languages always want to use this camel case where the words are right up against each other, and you divide the words by each new word begins with a capital. And this is the only place in Python where we actually use camel case. So classes in Python are formed using class names in Python are using the same rules that are used, say, in Java. So begin with a capital, then the rest of the word is in lowercase, and then each subsequent word begins with a capital. Okay, that's the only thing that's the camel case in all the Python world. Class is one of the reserved words. That means it's a Python keyword. Okay. This is, because it's the class for party animal, this is the template for making party animal objects. So it's kind of the cookie cutter. Okay. And the objects that we create are kind of the cookies. Okay. Each party animal object has a bit of data. So these variables that we declare inside the class, there's a couple of ways to do it, but the easiest and the clearest is just inside the class, but not inside any of the methods. We assign a value to a variable name. And this creates what we call instance variables. These will be one per instance, right? So let's say that we instantiate or we create 4 instances of a party animal. Okay, each of them in the beginning are going to have a little bit of data called X, and it's going to have the initial value 0. One of the things you're going to see in a minute, the party method is going to increment that value every time we call it. So over time, if we call a party on instance 1 4 times and we call it on instance 2 1 time, well then the X in instance 1 is going to be equal to 4, and the X in instance 2 is going to be equal to 1. So there's one set of these instance variables per instance. That's why we call them instance variables. The next thing is we have a method, and this one is called party. Okay, we define it pretty much the same way that we create a function. The only difference, well, one is that it occurs inside of the class. It's indented one indent. Okay, that's how we know that it's part of that class. Okay, and the first parameter that every method always gets is self, and self is a reference to the instance that we're in right now. More on that a little bit later. Okay. So then how do you refer to the X that's the instance variable for this instance? Well, you refer to it as self.x. So if we want to, when we party, increment this X by 1, well, we can do it by saying self.x gets assigned self.x plus 1. And then if we wanted to print the current value, we could print so far self.x. Okay, so this is a typical method. Okay, now what's this code down here? Well, it's not part of the class. As you can see, it's not indented under the class. This is a code that's going to use the class. Now, would we normally have them in the same file? No, we typically wouldn't. One of the reasons that we use classes is we want to share them among programs. And so we typically define classes in a separate module and we import it, and then we use the class. Well, that's hard to show on a slide. okay? Especially when you're just learning about classes the first time. So what we're seeing here is, what would it look like if you defined the class and used it in the same file, even though that's not the typical use case? All right. So what's going on here? So the variable name this he's using is n. So I guess this is like an instance. Okay, that's what we've n. It gets assigned, and when we just have a call to party animal, um, when you use the name of the class with parens, it creates a new instance. So by calling, um, we call this calling the constructor, and we'll get more details on what a constructor is in a couple of minutes. We will create a new party animal instance. Okay? And then we call the party method 3 times. Okay? Um, so the code on the right is another way to call the party method on the instance pointed to by n. It's not one that I use, and it's not one that I recommend, but it's one that's here on the slide, and it might be in the book. Okay? Now, let's just talk a second about what a party animal is. Well, the author of the book, Chuck Severance, he teaches at the iSchool at Michigan, which is a Big Ten school. And the Big Ten schools, and I teach at the iSchool at Illinois, and Big Ten schools are very big on football, and we'll get to that later. And they also have a reputation for partying. Okay, and one's interpretation of partying could vary. So there might be people who party by just exuberant behavior. Okay, but then there could also be people who use intoxicants. Okay, and some Big Ten schools have a pretty big reputation for being party schools, so they also have a reputation for high academic achievement. And how people can do that at the same time, I always wonder, but somehow they seem to be able to do it. So I think when we have a method, a party, we're expecting that whoever this party animal is, they're at least indulging in exuberant behavior and perhaps consuming intoxicants. I don't know. It's possible. Okay? So here's what I'm going to do. I'm going to show you another version of this that I created that'd be more like the code that you see in my class. Okay? So here's what I've done. I've created a module that's just going to hold this a class, and I called it mypartyanimals1.py. Okay, now why did I call it that? Well, that's kind of a scheme that I use in my class. Is this a scheme that people use in industry? No, probably not. Each workplace probably has a scheme for the way that they name their library modules. And when you're there, you would conform to that. But I name these my something, and I've got 4 versions here. So this one is my party animals 1 because it's the first one. And modules like this typically have a doc string. This one just says module contains the party animal class and related code, but probably would be longer than this. And each of the classes that are in it has a doc string. So it says class to represent a party animal, perhaps from a Big Ten institution. Okay, a little fun with uh, Michigan and Illinois, I guess. And again, a properly documented class would have more doc strings. It would be a doc string for each of the methods, and I just didn't want to clutter it up so much, right? One of the things I've done is I understand that in the slide we want to use short variable names because it's very hard to cram the code onto a slide, but this X, it has to represent something, okay? And I'm going to call it party count, okay? So I refactored this and I refactored X into party count, okay? Party as the name of the method, I think it's a decent idea. So it's a verb at least. Okay. Every time we party, we're incrementing the counter, party count. And what I decided to do is I use this plus equal syntax, which I prefer. So I just wanted to show you that. And one of the things I didn't do is I didn't turn this into an F string. So let's turn this into an F string. Normally, I would have turned this into an F string. So let's do this. So in my class, we're using F strings for just about everything now. So it would have looked like that. Okay. All right. So that looks a little better. I'm probably going to have to do that on all four of them. Apologize for that. Okay, so where do we call it? Well, typically we import this class into another Python file, and usually when we have a code that imports other code, particularly classes, but also functions, and uses them, we call this code the client code because it's using this library code, right? So I called this party client 1. So my docstring, a program to demonstrate the use of the party animal class, and then I have an import from party animals 1 import party animal. And then in my class, we always put the code into a main, and then we call the main. Okay. Can you have executable code that's not in a function? Well, sure you can. We see that we've got the call to main there. Is it a good practice to have a lot of it there? We don't believe so. Okay, so we've refactored this to be a more formal program. Okay, now instead of n, okay, I decided that we would call these instances, I use the variable a party animal instance. Okay, now that's a little long, but it's better than n. Okay, and then gets assigned. We have a call to party animal that constructs a party animal instance. And then we call party 3 times. Okay, now let's run this. What does it do? Well, I forgot. Well, you have to get your code to work together. I turn it into a string, not an F string. So here's an F string. Okay, now let's come back here and run this again. Okay, so far 1, so far 2, so far 3. So you can see that this one instance, the one that we are holding a reference to in the variable, a party animal instance, it has its own instance variable party count, And every time we call party on this instance, it increments it one higher and it prints out the result. Okay? So this really does the same thing that we just saw, but in a more professional developer friendly version that I created through the magic of refactoring. Okay? All right, on with the slideshow. So I think that we're just showing this thing executing. When we begin, this an variable is associated with an instance, and that instance holds the it holds the data. Okay, so he was calling the variable x, so it's equal to 0 to begin. And you can think of it as also holding the code for each of the methods. Now, it doesn't take a lot of thinking before you realize, well, if we copy the code into each instance, aren't we going to use up a lot of memory? And we would, except that we just have a pointer to the code here. So there's only one copy of the code for all of the instances, but it's kind of logically here. Okay. And then we call it party one. We call it a party, and we get so far one, so far two, so far three. And we saw that that's how the refactored version behaved as well. Okay. Now let's play with the dir and type functions in order to learn a little bit more. Okay. Remember how we said that we could use these for the built-in classes, and we could also use them for custom classes. So the dir command lists capabilities. So y is a list. We ask for the type of y, class list. We do a dir on y. And now we're seeing a list of methods. So these ones up front with double underscores before and after the name are dundered. Okay, double underscore, they're dundered. And dundered methods take on a special role. We don't call them directly. So they're called by the Python infrastructure. Okay, now if we're writing a very complex and complicated class, well, then we would have to provide a lot of these. Okay, but we're certainly not going to call them directly. You're not supposed to. Okay, so we're not emphasizing these, but we are going to emphasize the ones that are have regular names. They're not dundered, and that we call all the time. And again, ones that we use a lot includes append, count, and sort, and perhaps reverse if we want to put it into the opposite order. Okay. So we can use dir to find the capabilities of our newly created class. So one of the interesting things about these modern programming languages is the parts that you build kind of extend the language. Okay, so the built-in classes, we can query what their capabilities are by calling dir, and we can do the same thing for our custom class. So here's our custom class over here. Okay. And so we say that we want to print a type and the type of an, and dir and the dir of an. So the type of an is class main.partyAnimal. Well, ours, it'd be a little different in mine because it wouldn't be part of main, my refactored version. And then dir, we have a class, and we have a lot of other things here. We can see the instance variable x. Instance variables show up in the list as well, but we can see the method party. So we could use the dir to do research about the properties of a class that we wrote or that um, someone else had written. So try a dir with a string. Okay, so you can see here we created a string called the hello there, and we call dir. And again, strings have a bunch of dundered methods. As a user, we're not so concerned about them because we never call them directly. And then we've got things that we know about. Capitalize, ends with, is upper, is title, split. We've seen it all. Okay. Okay. So far we know that when we use a class and we create a new instance of a class, we get an object. Okay, and that object is a combination of data and behavior. Okay, and the data is going to be held in the instance variables, and the behavior is going to be represented by the code that's in the methods, right? Uh, we also know that each instance has their own copy of the instance variable or instance variables. Okay, so, but how do they come into existence? Like, what are the details of how do you create a new one? And do they ever go out of existence? Well, let's go explore that. So objects are created, used, and discarded. So sounds like they go out. Well, we discard them at least. Do they go out of existence? We have special blocks of code within our classes called methods that get called. There's one that gets called for us at the moment of creation. It's called a constructor. And then there's another one that doesn't get used often at the moment of destruction. It's called a destructor. Constructors are used a lot. Destructors are used very infrequently. Okay, but it helps us to understand the life cycle. So we code one in the next bit of code that we have, and then we can kind of watch the life cycle a little more closely. So constructor, the primary purpose of the constructor is to set up some instance variables to have the proper initial values when the object is created. Okay, so for me, the best way to think about this block of code, which looks a lot like a function, it's a method that we call the constructor. The best way to think of it is this. When we are constructing a new a dog, right? Okay, it's the dog class, right? The Python infrastructure creates the object, okay, but it's not fully decorated, okay. We have an opportunity to set initial values in this method that we call the constructor. So does the constructor actually slam down the cookie cutter and slice out a snowman shaped piece of dough? Probably not. By the time we get to the method that we call the constructor, the dough's probably already been stamped out, and we're going to set initial values for things. So for me, when I'm thinking of the cookie metaphor, and I've got a bigger version of this here, in my mind, right before the constructor method gets the control, the Python infrastructure has picked up this cookie cutter and slammed it down and created a blank piece of dough. Okay. And now in the constructor, we're going to decorate it. It's not called a decorator. And in fact, there are things in object-oriented software called decorators, and they do something completely different than this. But metaphorically, okay, the constructor doesn't do anything. We won't see any code that stamps out the dough, but we will see code that gives things initial values. All right, so let's see it. I promised it. Let's deliver. Okay, so the constructor for a class is a dundered method called init. Okay, why a dundered method called init? Well, the Python infrastructure has to know what to call. It has to know what the constructor is named. So we give it a standard name. Now, are users supposed to call dunder init directly? No, they're not. That's why we dundered it. Okay. This gets called implicitly when we create a new instance. So we're not going to decorate this. Instead, because we are exploring the life cycle, we've created two methods, the dunder methods that we've added. We already had party, right? We've added dunder init, and we're also adding a dunder del for delete. Okay, so dunder init is the constructor, dunder del is the destructor, and the only thing we have them doing is printing a lifecycle message to help you and I envision how these instances come into being and go out of being. Okay, now would a real class print these kinds of things? No, it never would. Okay, this is a demonstrator class. Well, what would typically happen in a init? Well, what would typically happen, instead of printing a lifecycle message, we would make sure that we properly initialized all the instance variables. Okay, and you'll see why we're going to do more than what's done up here in this x gets assigned 0. What would we do in a destructor? Well, I have to think hard because I've probably only coded one in all the years that I've been doing object-oriented programming, which is probably 25, something like that. Okay, but this is the kind of thing where you just need to clean up some kind of resource. Sometimes you might have some object that represents a row in a database table, okay? And maybe that value has changed, but we never wrote it back to the database, okay? The kind of thing that you would do in a del would be to check if this has been written back to the database, and if not, write it back to the database before it blinks out of existence. Oh, okay, so that's what these things are. So okay, and we have the client code in the same file, which is not to say that's a typical thing, but that's a convenient thing for these learning examples. So we construct a party animal. We put the references in AN. We call party. We call party. Now the next thing that we do is that we assign a 42 to AN. Okay. So AN has taken on a new value. Okay. Well, is it pointing to or referring to this instance of party animal any longer? No, it's not. So uh, it makes it a target for something called garbage collection. Okay. And the garbage collector runs reasonably often. It's not always as soon as you. So, what's the garbage collection? It keeps instances of objects that we're no longer using from cluttering up the space used by our program. Okay. So it keeps a counter. This is cool. The Python infrastructure keeps a counter for every object that says how many things are pointing to me, how many variables are referencing this instance. As soon as that goes down to zero, then that instance is a candidate for garbage collection. And the next time the garbage collector runs, right before it gets rid of the space, it calls del. Okay. Um, and then the last thing that we're doing is that we're printing uh, n it contains n. Okay. And are we expecting to see an instance of the party animal class here, or are we expecting to see a 42? Well, let's just see what the output was. So we constructed a party animal, and we got uh, the life cycle message, I am constructed. And then we called a party on it twice. So we got so far one and so far two. Okay. Then we assigned a 42 to n. So now the there there are no variables in the program that have a reference to that party animal object. And what happened is when the garbage collector ran, which was immediate in this case, um, it called del because it's going through the list of objects. You go, oh, here's one that doesn't that the pointer counter has gone down to zero. Let's call del. Does it have a del? Yes, it has a del. Call del. Then we get the message. I am destructed too. And then it gets rid of the space so we can reclaim the space in the memory. And then when we print and it contains n, we're referring to this 42 integer object. Okay. Now, how would this look if we refactored it a bit? Okay. So I just want to say, if we were not constrained by what fits on a slide, okay, let's look at what we have. So I've got a second version of my party animals 2. And in addition to say, module contains the party animal class and later code, I also say this version, it contains init and del methods that display lifecycle messages. And most of this looks the same except there's an init and a del, and you can see that they just do a print. Okay, so we haven't changed much at all here. Okay, again, I turn the X into party count so it reads a little better. So let's go to party client 2. Okay, and again, it's saying from party animals 2, we have to import from the new version, import party animal. So I wanted to use an arbitrary variable name instead of instead of n or whatever we called it, I just called it some variable. So some variable gets a new party animal object. We call party on it twice. Then we assign a 42 to that some variable. That's going to orphan that party animal object without anything referring to it. So it's going to make it ready for garbage collection. And then we're going to, so we should be getting, shortly after them, that we should be getting the end of life cycle message from the Dell. And then we print some variable contains some variable, and in this case I change this into use an F string, which is a little more modern. So if we run this, what do we get? I am constructed, so far 1, so far 2. I am destructed 2, some variable contains 42. Just what we expected. But, kind of cleaned up and refactored for the benefits of the students in my course. Okay, let's get on with the slideshow. More about the constructor. So in object-oriented programming, a constructor in a class is a special block of statements called when an object is created. And I always like to be a little bit more specific here. Called just after an object is created. So they stamp the cookie out of the electrons and then they run the constructor. Okay. We have many instances. Okay, that's where the value, there are classes that we only create one instance of. There's a pattern for this called the singleton, but it's the gross exception. Typically, when we use a class, we're going to create many instances. So we can create lots of objects. The class is the template for the object. We can store each distinct object in its own variable. We call this having multiple instances of the same class. Each instance has its own copy of the instance variables for that instance. Okay, they have their own values. They may all, so they all have their own values. Okay. Each instance also has a copy. You can think of it as having a copy of all the methods. It really has a copy of the pointers to all the methods. So we don't create multiple copies of the methods in all the instances. That would just clog up lots of memory. But you can think of it that way. Okay, so so you might ask yourself, we said, well, we don't have a lot of destructors, right? We also said, the constructor printing out a lifecycle message, that's not what it really does. We just wanted you to see the lifecycle. So that raises the question, well, what the heck do constructors actually do? Okay, and constructors can have additional parameters. All the calls to constructors that we've seen so far just had empty parens in the calling code. Okay, well, we can pass actual parameters, and then the constructor method, the init, the dunder init, can set the values. So every time that we create an instance, we can create it with just the values for the instance of variables that we would like it to have. Okay, so how does this work? Well, this is a little crammed together, and my refactored version will be a little bit easier to read, but this is class party animal. We have an instance variable x, which we set to 0. We have a new instance variable name, which we sent to the empty string, okay? Uh, Now we have a constructor. It has a header and 2 lines. And you can see that in addition to this kind of built-in first formal parameter that we have of self that we always have on these um, methods, right? And again, what does self refer to? It refers to this instance that we're in right now, okay? But we're also passing in z. Now, z is a horrible variable name, but you have to give the author credit for getting all of this onto a slide, which I'll tell you from experience is darn hard to do. Okay, so Z is going to be the name. Okay, so what do? Well, we take each of the values that we've been passed and we set the instance variables to that value. So we call with a name. We call the constructor with a name, and then in the init we set self.name to that value. And then of course we're still printing a lifecycle of message just because we can. Okay? And now we've changed a party to make it a little more user friendly. We've included the name in the print that we put where we say what the party count is. Okay. And again, we've got the client code in this same file, not because this is typical practice, but because this is a learning example. So we construct a party animal passing in the name Sally, and we save the reference in the variable S. We do the same thing for Jim, and we put it in the variable J. So we call a party on S. We call a party on J. We call a party again on S. So we'll have called a party on S twice and only once on J. So let's look at that in the refactored version, okay? And again, I've got a lot more room here than the author has on the slide, okay? So the first thing that we're looking is the new version of my party animals. This is the kind of library module that's holding the classes related to party animals. So module contains the party animal class and related code. This version contains a constructor that sets the value of the variable name. This version prints the name in the party method. Now, would I put this in production code? No, this is just a kind of play-by-play that an instructor will put into comments. Okay, and then we come down here and we're doing the same thing. Now, I decided that X was refactored into party count. Name is a great variable name, so we left that the same. We gave that the empty string. Now, the constructor. When he wrote the constructor on the slide, here, instead of name, he used Z. And that's because that's all he was confident was going to fit on the slide. Okay. And he also wanted to emphasize that it doesn't have to be the same word as the instance variable name. There's no magic matchup by name. What we're doing is, this is just a plain old a plain old formal parameter, and it gets matched up with the actual parameter on the calling code. Now, what some people will do is that they'll give uh, they'll use a different thing here. So uh, I saw a version of his code that I found online where instead of spelling name on this formal parameter list with an E, he left the E off. Oh, okay. Now you can reuse it. The parameter name, NAME, and the instance variable name, which we refer to as self.name, are two different things. And so we can actually assign what's in the parameter to the instance variable with self.name gets assigned name. Some people don't like that, and they'll put something like, this name, or something like that, or a name, or the name, okay? And then they'll use that. I just want to let you know you can use the same word because self.name and the parameter name are two different things, and Python does not get confused. And then he puts out the message, the lifecycle message, and then down here in party when we do the print, again, we use an F string and we refer to the name from the instance variable as self.name, and we refer to the party count as self.partyCount. So when we come over to um, party client 3, okay, we're doing the same thing. I decided that I had the room to use the names for the variable names. So instead of S and J, I call them Sally and Jim because I wasn't afraid of running out of slide. Okay, so I called party animal. So when you call the constructor, when you construct a new instance of a class, you don't call init on it. Okay, you use the name of the class. That's how you call the constructor. And then you pass in whatever actual parameters you're expecting. And I just want to point out, you never code self on the calling code. Self just automatically appears through the magic of Python infrastructure on the called code. Okay, so here we are. We construct a Sally, we construct a Jim, we call a party on Sally, a party on Jim, and then a party on Sally. So when we run this, we get Sally constructed, Jim constructed, Sally party count 1, Jim party count 1, Sally party count 2. So here you can really see that each instance gets its own copy of the instance variables because not only are these instances associated with different people names, but they also have the appropriately different party counts. Okay, so each instance has its own instance variables. That's why we call them instance variables. Okay, back to the slides. Well, this is a play-by-play on how all that happened, and I'm just gonna go past that. Now, there's a whole lot to talk about when we're talking about custom classes or even the built-in classes. So, we can only touch on so many things. But one of the things that can be done with classes that is super powerful is the use of what we call inheritance. And inheritance is the word that we use to describe the use of superclasses and subclasses. Okay, so now we're going to talk about that and give some examples. When we make a new class, we can reuse an existing class and inherit all the capabilities of an existing class and then add our own little bit to make our new class. It's another form of store and reuse. It keeps us from having to clone one class into the next, right? If in fact we have classes that we want to build, we have 3 or 4 things that we want to build, and they all have common properties. What we can do is that we can extract the common things and put them in a superclass. And that turns out to be a much more manageable way to maintain these classes over time. Uh, uh, the new class, the child, has all the capabilities of the old class, the parent, and then some more. And I really like the way the author is using the term child and parent, because the formal names that are given in object-oriented technology, the formal name for the parent is superclass, and the formal name for the child is subclass. And you can get kind of turned around by those names. So let's say that we were talking about heroes, right? So we would have a normal hero. Um, um, I don't know who that would be. Some hero from, from fiction, right? And then we have a superhero from fiction, right? So we would think of a superhero from fiction would be somebody like Superman, right? And how would we relate the capabilities of a hero and a superhero? Well, they're both great people with admirable character and great behavior, but the superhero has more powers. They can fly, they can lift a lot of weight, they're invisible, they can travel through time. We all know about superheroes, right? So superheroes are more powerful than subheroes, right? Yeah, or more powerful than heroes, right? Now, in this inheritance, the original class, the parent, okay, it's called the superclass. And then the derived class, the one that inherits from the parent, the child, that's called the subclass. But really, the way, when you think of their capabilities, the child has more capabilities than the parent. And the sentence, the last of the sentences on the slide says exactly that. The new class, the child, has all the capabilities of the old class, the parent, and then some more. And what I like to think of is, I've got children. They're 35 now. They're twin girls who are lovely and capable women. But as a parent, I think I hope for what most parents hope for. I hope that they can do everything that I can do and that they can do more. So my hope for them is that they get all my good qualities, none of my bad qualities, and that they have all these extra capabilities. That's my wish for them. So these names, a parent and child, are perfect. Superclass and subclass, which are more typically used, and we'll be using it, if you think of it in terms of hero and superhero, you'll get it backwards because it's the subclass that's more powerful than the superclass. It has all the powers of the superclass plus more. Okay? So, subclasses are more specialized versions of a class which inherit attributes and behaviors from their parent classes and can introduce their own. More powerful. They know more, they can do more. That's what I want for my children. Okay, so let's look at an example of this. And again, I think we're trying to be fun. Again, um, we're kind of doing Big Ten football. Okay, so we have a party animal class. Okay, and now here's what we want to do. We want to define a football fan class that's a subclass of party animal. So the syntax for that is um, if we want it to be a subclass of a superclass, we just say football fan, and in parens we put party animal. Okay. Notice that superclasses don't know that they're superclasses. So top level classes don't have to have these parens. You don't give them empty parens. You only add the parens when you've got something to say. Okay. And that there's nothing in party animal that says that it has the the subclass football fan. It doesn't know. Okay. Okay. So what can, I'm so sorry. Let me back up. Here it is. That's where I was. What can, what does football fan know the party animal does not? Okay. Well, it, it, it inherits uh, the instance variables that party animal has. So it knows about X, it knows about name, but it also knows about points. These are football points. And then behavior wise, what can it do that a party animal can't? Well, it inherits party from party animal, but in addition, it's got a touchdown. This is sort of a touchdown celebration that the fans would do. Okay, in which case it adds 7 to the points. So in American football, if you score a touchdown and you kick the 1 point extra point, uh, you score 6 points plus 1, which is equal to 7. So a touchdown and the extra point are equal to 7. So we're assuming that they always get the extra point. So we call a touchdown, we add 7 to points. We call party, so you can call methods that are already there, and then we print self.name points self.points. Okay, so it knows everything the party animal knows plus more. And it can do everything that party animal can do plus more. Okay? And you can see how it's more capable. Subclasses are more capable than super classes, right? And then again, he's got some of the client code in the same file. So he creates a party animal, Sally, keeps a reference in S, and calls a party. And then a football fan, Jim, saves that in J. He calls a party on J, and then touchdown. So we're kind of walking through. I'm sorry. I don't know how that happened. Yeah. Okay. So we can't walk through the individual parts. Okay. So, lucky enough for you, I have created the last of my refactored versions over here. I've got my party animals 4. Okay. And let's look at this. So again, I'm keeping all of the shareable code in its own library-esque kind of module. Okay, but that's the typical good practice. You typically are creating these classes because you want to use them in more than one program. So you don't want to combine the programs with the classes. Uh, you want to have the classes in some kind of library module, and then each of the programs is its own .py file and its client code that uses one or more of the classes from the library module. So the party animal hasn't changed. Okay, what I did say, I changed the doc string that says module contains the party animal class, its subclasses, and related code. And again, there probably would be more details here if this were a real production quality set of doc strings. Okay, so then uh, party animal class is the same. Football fan uh, uh, in the parens party animal, and then my doc string subclass of party animal parties at football games, perhaps supports a Big Ten team. Okay, I'll keep the metaphor going. All right. So it has this new instance variable points. It has an initial value of 0. Okay. Um, and one of the things that I didn't like is I didn't like the name touchdown for a method name because it didn't involve a verb. A touchdown is a noun. Okay, so for people trying to understand my class, it's very important when I design the methods and I give them a name that they have a verb or verb phrase kind of names. So what I decided is that this should be called party after touchdown. Okay, because it's more partying. Okay, but it's more intense because they just scored a touchdown. So then we uh, we sum the points. Again, I use the plus equal because I think it reads better. We do call party on ourselves, and then we print self.name points, self.points. Okay, and then I've got the client. So I've got party client 4. Okay, and what did I do? Well, I use more meaningful variable names. So instead of S and J, I use Sally and Jim. Okay, so here's what I did. I constructed the object for Sally and I called a party on it. I constructed the object for Jim. I called party and then I called party after touchdown twice, which is a little bit more than was done in the author's slides. Okay, but let's look what happens. Okay, so let's look here. So we get Sally constructed, Sally party count 1, Jim constructed, Jim party count 1, Jim party count 2. That's when we called party after touchdown. Jim points 7, and then we called party after touchdown again. Jim party count 3, Jim points 14. Okay, so it works about as you would think. All right. So we've done kind of it's silly things here. Partying about Big Ten football, but hopefully this this will help you get acclimated with the whole thing. So definitions. Is that the end? Yeah. So a class. So a class is a template or blueprint. Okay. So best thought of in this picture metaphor, best thought of as the cookie cutter itself. Okay. Uh, Classes have um, well, they have instance variables and they have methods. Okay. Now, the word attribute is kind of a funny word. There is one way that people use the word attribute, and they mean it to refer to the instance variables. But there's a wider use of attribute in Python that includes both instance variables and methods. So I'm not fond of this. I like to say instance variable method. An object is a particular instance of a class. So instance, object, same deal. A constructor is a code that runs when an object is created. And again, what part of the creation of the object? Well, the Python infrastructure picks up this class cookie cutter and stamps out a blank cookie, a snowman without any icing on it or any little beads or anything that. Then it runs the constructor. What would the constructor do in the metaphor? It probably would put on the icing and the beads. Okay, so it's an initializer. Inheritance is the ability to extend a class to make a new class. Okay, and the key thing to remember here is it's probably more useful to think about the parent class and the child class, because the child is more powerful than the parent. And we want to think about that in both of them in their long-term adult lives. Okay. And the fact is, the subclasses are more powerful than super classes, and that's kind of counterintuitive, but that's the way it works. In summary, object-oriented programming is a very structured approach to code reuse, indeed. And we can group data and functionality together and create many independent instances of a class. And it's kind of interesting for me. I've been hanging around programming now for a little over 50 years. And probably the first 20 of those, I wasn't using object-oriented programming languages. And I was missing things that operated the way these object-oriented programming languages operate. So these objects, there's a lot of details to remember in the way they work, but if the old me, the me of 45 years ago could get his hands on an object-oriented programming language like Python, he would have been a very happy young man. And that's it. We've got the credits, and we have a link to the cookie cutter photo. And I really like the cookie cutter photo. Okay. I like the big version that we link to here, because I think that the metaphor is just perfect as long as you know what to match up with what in the metaphor. And then we have another link to a Lassie picture. Unfortunately, the picture that they link to is, I thought, was Lassie and Timmy, and yet when you look at the caption, it says, Lassie watches as Jeff works on his bike. And I'm saying, Jeff? I thought that guy didn't look like Timmy. And in fact, there was another character who I didn't really remember who was Jeff, played by Tommy Reddick. So then I went to Wikipedia and I clicked through on the photos and I found the picture I already showed you of Lassie and Timmy. Okay. And that's the real deal. Okay. And they loved each other. And Timmy always got into a bind, and Lassie always got uh, Timmy out of trouble, usually by calling the grown-ups, going to get the grown-ups. And the classic is the one where Timmy gets stuck in the well. And with that picture of Lassie and Timmy and the story of Timmy stuck in the well, I'm going to say bye until next time. Bye-bye.